Assalamualaikum everyone and a very good day to all. In this video, we shall learn about the schemes and techniques that we use to transmit data digitally. First, we will discuss digital to digital conversion techniques. This is the method which converts digital data to digital signals. We will also learn about line coding and the different types of coding schemes. Here is the table of contents for you to navigate through this video. So as we saw from previous chapter, we discussed about data and signals, and data can be either digital or analog. Same goes to signals. It can be represented, it can be representing data in terms of digital or analog. In this chapter, we will see how we can represent digital data by using digital signals. There are basically three different techniques for the conversion, and they are line coding, block coding, and scrambling. Line coding is always needed, whereas block coding and scrambling may or may not be needed. So what is line coding? Line coding is the process of converting digital data to digital signal. So you can assume that data, it can be in terms of images or video or text, and they are all stored in the computer memory as sequences of bits, meaning zeros and ones. So the line coding converts a sequence of bits to a digital signal. Okay, as you can see here at the sender, digital data are encoded into a digital signal, and at the receiver, the digital data are recreated by decoding the digital signal. So that means that the line coding encoded the digital data into a digital signal, and it also can be decoded at the receiver. Before we discuss the different line coding schemes, we shall address their common characteristics. So these are the list of their common characteristics, meaning that in every line coding schemes, all of these characteristics are there, such as signal element versus data element, their bandwidth. So every line coding would have different kind of bandwidth, or whether they have DC components or not, whether they have self-synchronization or not, and so on. So a data element is the smallest entity that can represent a piece of information, meaning that it is the bit, okay, either 0 or 1. In digital data communication, a signal element carries data elements. So this data element is to be carried by the signal element. A signal element is the shortest unit in time-wise of a digital signal, meaning that in other words, the data elements are what we need to send, and signal elements are what we can send. Data elements are being carried, and signal elements are the carriers. Okay, we can define a ratio of R, which is the number of data elements carried by each signal element. Okay. Okay, let's see some examples to help distinguish between signal element and data element. So in case A, we have one data element per one signal element, and from there we can calculate R, the ratio equals to 1. And for B, we have one data element being carried by two signal elements. This extra actually signal elements will help with synchronization, and from there we can calculate R equals to 1 over 2. In case C, we can see that two data elements is being carried by one signal element, and 2 divided by 1 you get 2. And in case D, you can see that a group of 4 bits is being carried by a group of 3 signal elements. So from here you can calculate R, which is the number of data elements carried by each signal element equals to 4 over 3. Okay. Can give an analogy here. Suppose that each data element is a person who needs to be carried from one place to another, and the signal element, we can think of it as a vehicle, a car that can carry people. Okay, and when we have R equals to 1, that means that there's only one person driving in one car, whereas when we have R more than one, it means that more than one person is traveling in that car, meaning they are doing a carpool. And we can also have the case where one person is driving a car and a trailer. That means that it's two vehicles, right, connected together. And this is the case where we have R equals to 1/2. Data rate and signal rate are also the characteristic that we need to be clear about. Data rate defines the number of data elements or bits sent in 1 second, and the unit is bits per second, whereas the signal rate is the number of signal elements sent in 1 second, and the unit is the baud. The data rate sometimes being called as bit rate, and the signal rate is sometimes called the pulse rate or the modulation rate or the baud rate. Okay, and one of the goals in data communication is to increase the data rate while decreasing the signal rate. Okay, so we want to increase data rate but decrease the signal rate, and we can imagine this in terms of the analogy that we have just now. We want to reduce the traffic jam, so we want to have as many carpools as possible. Okay, so we have a greater number of people within a car, but we want to make the car lesser on the roads. Okay, by increasing the data rate, it increases the speed of transmission. Okay, so no traffic jam, and decreasing the signal rate, meaning that it will decrease the bandwidth requirement. Okay. Okay, now we need to consider the relationship between the data rate and the signal rate. Data rate is being represented by capital N and signal rate is by S, and we also have R within the equation, which has been previously defined, which is the number of data elements carried by each signal element, and the relationship of S equals to N over R, of course, depends on the value of R. Okay, it also depends on the data pattern. If we have a data pattern of all ones or all zeros, the signal rate may be different from a data pattern of alternating zeros and ones. Okay, so to derive a formula for the relationship, we need to define three cases: the worst, best, and average. The worst case is when we need the maximum signal rate, and the best case is when we need the minimum. In data communications, we are usually interested in the average case, and we can formulate the relationship between the data rate and signal rate as S average equals to C times N times 1 over R baud. Okay, and again, the N is the data rate in bit per second, C is the case factor, either it's worst, best, or average, and S is the number of signal elements per second. And again, R is the number of data elements carried by each signal element, the ratio. And as you can see here, we can have different scenarios. And as mentioned just now, in data communication, we're interested in the average cases. So typically, C will be given as 0.5. Let's do an example. So we have a signal is carrying a data in which one data element is encoded as one signal element, meaning the ratio equals to 1. And given the bit rate is 100 kilobit per second, so calculate the average value of the baud rate. Remember, baud rate is also meaning the signal rate, and C is given between 0 and 1. Okay, we can assume that C is half 1/2, and we can calculate the baud rate as using previous equation as equals to C times N times 1 over R, and we have C 1/2, we have N 100 kilobit per second, and the ratio is 1, so 1/1, and we'll get equals to 50,000 or 50 kilo baud. Okay, let's go to the next characteristic, which is the bandwidth. If you recall, a digital signal that carries information is non-periodic. Okay, you can see that bandwidth of a non-periodic signal is continuous with an infinite range. However, most digital signals we encounter in real life have a bandwidth with finite values. So the effective bandwidth is finite. In other words, the bandwidth is theoretical infinite, but many of the components have such small amplitude that can be ignored. Okay, so the effective bandwidth is finite. From now on, we will talk about the bandwidth of a digital signal. We need to remember that we are talking about this effective bandwidth. Okay, we can also say that the baud rate, not the bit rate, the baud rate determines the required bandwidth for a digital signal. Okay, if you use the analogy just now, the number of vehicles, not the people inside the vehicle, affects the traffic. So that means that the baud rate affects the traffic, or affect the bandwidth. Okay, so as you can see, the bandwidth also reflects the range of frequencies that we need. So there is a relationship between the baud rate or the signal rate and the bandwidth. The bandwidth is actually a complex idea. When we talk about bandwidth, we normally define a range of frequencies, but we need to know where this range is located, as well as the values of the lowest and the highest frequencies. In addition, the amplitude, if not the phase, okay, of each component is also important. In other words, we need more information about the bandwidth than just its value. We need a diagram of the bandwidth, and I will show you the bandwidth for most schemes that we will discuss later in this video. For the moment, we can say that the bandwidth or range of frequencies is proportional to the signal rate or the baud rate, and you can see the equation is similar like just now, because the baud rate is proportional to the bandwidth. Okay, so the minimum bandwidth can be given as B min equals to C times N times 1 over R, and we can solve for the maximum data rate if you rearrange the equation, where maximum data rate equals to 1 over C times B times R. Of course, if the bandwidth of the channel is given. Okay, if you still remember, we learned about the maximum data rate of a channel, of a noiseless channel, Nyquist formula, and max equals to 2 times B times log 2L. And here we want to see whether it agrees with the formula for that maximum data rate. Okay, so a signal with L levels actually can carry log to L bits per level. That means that for each level it corresponds to one signal element, and we assume that the average case is C equals to half. Then we can have N max equals to 1 over C times B times R, which is equals to, if you look at 1 over C equals to 1 over 2, so it becomes 2, and times B, and R is, again, as I mentioned just now, we can assume that it corresponds to number of levels. With L levels, we can carry L to L, and as you can see here, it actually agrees with the formula for maximum data rate. The next characteristic is the baseline wandering. So when we decode a digital signal, the receiver will calculate a running average of the received signal power. Okay, so this is what we call baseline. So the incoming signal power is evaluated against this baseline to determine the value of the data element. If you have a long string of zeros or ones, this can cause a drift in the baseline, and this is what we call baseline wandering. Okay, the slight drift, and it will make it difficult for the receiver to decode correctly. Any good line encoding scheme, we need to prevent this baseline wandering. So we need to prevent a long string of zeros or ones. The next characteristic is the DC components. Okay, when we have voltage level in digital signal that is constant for a while, these spectrums creates very low frequencies, results of Fourier analysis. Okay, and this frequency are around 0, and they are called DC or direct current components. And this frequency will present problems for a system that cannot pass low frequencies, or a system that uses electrical coupling via a transformer. And we can see that DC component means 0 or 1 parity that can cause baseline wandering. Okay, so there is a relationship there. For example, a telephone line cannot pass frequencies below 200 Hz, and also a long distance link may use one or more transformers to isolate different parts of the line electrically. So for these systems, we need a scheme that have no DC component. Another characteristic is the self-synchronization. So in order to interpret the signals received from the sender, to interpret it correctly, the receiver's bit intervals must correspond exactly to the sender's bit intervals. So sometimes if the receiver clock is faster or slower, then the bit intervals would be unmatched. It will not match, and the receiver might misinterpret the signals. Okay, and this figure will show you how a situation when we have receiver that has a shorter bit duration. So in this particular case, we have sender sends 1011 0001, while the receiver will receive it wrongly as more bits information there. So a self-synchronization, synchronizing digital signal includes timing information in the data being transmitted, and this can be achieved if there are transmission in the signal that alert the receiver to the beginning, middle, or end of the pulse. Okay, if you remember just now we saw R equals to 1/2, and if the receiver's clock is out of synchronization, these points can reset the clock. Let's do an example on self-synchronization. So imagine in a digital transmission, the receiver clock is 0.1% faster than the sender clock. So how many extra bits per second does the receiver receive if the data rate is 1 kilobit per second? And what will happen if the data is greater at 1 megabit per second? So at 1 kilobit per second, the receiver receives 1001 bit per second instead of 1000 bit per second. Okay, so we can calculate from 0.1 divided by 100, which is 0.1%, multiply with the 1000 bit per second, and we get 1. So at 1000 bit sent, we receive 1001 bits received, which is 1 extra bit per second. And at 1 megabit per second, the receiver receives 1,001,000 bit per second instead of 1 million bit per second, or 1 megabit per second. Okay, so that means that we can get this from calculation again. 0.1% multiplied with 1 megabit per second, 1 million, we get 1000. So 1 million bit sent, 1,001,000 bit received. Therefore, we have 1000 extra bit for every second. Okay, so this is why self-synchronization is very, very important. Okay, the other three characteristics are built-in error detection, immunity to noise and interference, and also the complexity. So it is always desirable to have built-in error detecting capability to generate code to detect some of or all of the errors that occur during the transmission, and some encoding schemes will have this capability to some extent. And immunity to noise interference is another desirable characteristic. Okay, and a code that is immune to noise and other interferences. Okay, some of the encoding schemes that we will discuss will have this capability. And in terms of complexity, a complex scheme is definitely more costly to implement than a simpler one. And for example, a scheme that uses 4 signal levels is more difficult to interpret than one that uses only 2 levels. Before I end this video, please let me know how is your understanding on this topic throughout this video so far at this link. Your participation is highly appreciated. If you have any questions or comments, please let me know. Thank you and see you on the next video.